Hi. Welcome back. In this video, let us take a look what are some notable problems in fraud detection and why we want to investigate them. In today's world, fraud has become increasingly prevalent, affecting both businesses and public institutions. As a result, there is a growing need for automated fraud detection systems. These systems play a crucial role because human analysts often struggle to identify fraudulent patterns in transaction datasets. These datasets are typically vast, with numerous variables and frequent updates. Moreover, due to the relatively small number of fraudulent transactions compared to legitimate ones, the data distribution is unbalanced, meaning it is skewed towards non-fraudulent observations. This imbalance poses challenges for many learning algorithms, which tend to underperform when applied to unbalanced datasets. Researchers have proposed methods, such as resampling, to improve algorithm performance in such cases. Additionally, the complexity of fraud detection is influenced by the extent of overlap between the classes of interest, as transaction records may provide limited information about the nature of the fraudulent activity. Understanding these factors is crucial for developing effective fraud detection strategies. This research aims to address the existing gap by conducting a comprehensive comparison of numerous algorithms and modeling techniques using two real datasets. The focus is specifically on addressing open questions such as, which machine learning algorithm is the most suitable? Is it necessary to update the model daily, or is a monthly update sufficient? How many transactions are needed to effectively train the model? Should the data be analyzed in their original unbalanced form, or is there a better way to rebalance them? Additionally, the research aims to determine the most appropriate performance measure to assess the obtained results. In the field of fraud detection, we come across two types of techniques: supervised and unsupervised. Supervised techniques rely on the transaction's known class, such as genuine or fraudulent, and require reliable classifications of past transactions. However, these methods are often limited to identifying fraud patterns that have already been observed. On the other hand, unsupervised techniques aim to identify transactions that deviate the most from the usual patterns by modeling the distribution of the majority of transactions. Dealing with unbalanced datasets poses challenges in the learning process, as most learning systems are not designed to handle significant disparities in the number of cases between different classes. Traditional approaches in the literature address the issue of unbalanced datasets by utilizing sampling techniques to balance the dataset. Two main approaches can be distinguished: data-level methods and algorithmic-level methods. Data-level techniques involve balancing the dataset or reducing noise between the classes as a pre-processing step before applying any algorithms. On the other hand, algorithmic-level methods adapt the classification algorithms themselves to handle the detection of minority classes. In this article, the focus is placed on data-level sampling and ensemble techniques. In a binary classification problem, we often use a tool called a confusion matrix to assess the performance of our model. The confusion matrix helps us understand how well our model is predicting whether something is fraud or not. It compares the predictions made by our model with the actual ground truth. The confusion matrix is a table that shows 4 different outcomes: true fraud, true genuine, predicted fraud, and predicted genuine. The rows of the table represent the actual ground truth, while the columns represent the predictions made by our model. It helps us see how many cases our model correctly identified as fraud, true positives, TP, how many cases it wrongly identified as fraud, false positives, FP, how many cases it missed and didn't identify as fraud, false negatives, FN, and how many cases it correctly identified as not fraud, true negatives, TN. When dealing with unbalanced class problems, traditional assessment measures like true positive rate, TPR, true negative rate, TNR, and accuracy can be misleading. Instead, in fraud detection, we are more interested in two important measures: precision and recall. Precision tells us the proportion of correctly identified fraud cases out of all the cases our model predicted as fraud. Recall tells us the proportion of correctly identified fraud cases out of all the actual fraud cases in the dataset. In simple terms, precision focuses on how accurate our model is when it claims something is fraud, while recall focuses on how well our model can find all the fraud cases in the dataset. These measures help us evaluate the effectiveness of our fraud detection model and ensure we are detecting as many fraud cases as possible while minimizing false alarms. Although there are many other definitions out there, this framework remains to be the golden standard of the definition for today's binary classification problems. The situation of credit fraud detection can fall under this setup, and this way every scenario in the table is well defined. The goal is simple. We want to build a model such that it could predict this table very accurately. This means we want an AI model that says a user is fraud and they are actually fraud, and says a user is okay and they are actually okay, and no errors, to the best of its abilities.